The entire semiconductor world said it could not be done. Not in this decade. Not without the most advanced machines on Earth. And definitely not by a company that has been cut off from buying those machines for years. Huawei just announced a new way to build processors that rivals what 2-nanometer chips can deliver, without the machine that makes 2-nanometer chips possible. Without TSMC, without ASML, without any of the tools the rest of the industry depends on. One specific number in that announcement made every semiconductor engineer on the planet sit up straight. Not the performance claim, not the transistor density. A different number. 1005 microns. And once you understand what that number means, you will understand why engineers around the world are paying very close attention right now. The chip industry ran on one idea for 60 years. Make transistors smaller and everything gets better. That idea is slowing down. The gains that used to come every 2 years now take 3 or 4. And Huawei cannot even attempt that approach because America cut them off from the machines that make it possible. So Huawei asked a completely different question. What if transistor size is not the only way to make chips better? In this video, you are going to understand exactly what Huawei announced and why it matters. The 60-year rule that ran the world and why it is breaking down. The machine Huawei cannot buy and what they built instead. The one number that has the entire industry nervous. And the single unsolved problem that determines whether this is a real roadmap or a very impressive presentation. Subscribe, because the answer to that last question is where this story gets genuinely uncertain and genuinely important. The rule that ran the world for 60 years and why it is breaking. The entire technology industry ran on one idea. Make things smaller and everything else gets better. Smaller transistors mean faster chips. Faster chips mean better computers. Better computers mean better everything. This idea had a name, Moore's Law. And it worked so well for so long that the whole world assumed it would keep going forever. Every 2 years, engineers would figure out how to shrink transistors again, cram twice as many onto a chip, and performance would jump. Cost would drop. The cycle would repeat. We went from thousands of transistors on a chip in the 1970s to billions by the 2000s to hundreds of billions today. The chip inside a modern smartphone has more processing power than the supercomputers that filled entire rooms just a few decades ago. That is not a metaphor. That is just the math. But here is the part they do not put on the marketing slides. That streak is slowing down. The gains are getting smaller. TSMC is fighting for around 6% area improvement with their next generation. 6%. That used to be 50% or more. Building a new leading-edge chip factory today costs somewhere around $20 billion. A single generation of new transistor design can cost $1 billion in development before a single chip is made. In plain terms, the cheap gains are gone. The expensive ones are getting harder. And for Huawei, the problem is not just that progress is slowing. Their problem is far more specific. And it goes back to a decision made in Washington. The machine they cannot buy. And what they built instead. In 2019 and 2020, the US government placed sweeping restrictions on what technology companies could sell to Huawei. The restrictions kept getting tighter. By 2022, Huawei was essentially cut off from the most advanced chip manufacturing equipment in the world. The most important piece of that equipment is a machine called an UV lithography system, made by a Dutch company called ASML. And there is basically nothing else like it on Earth. This machine uses a laser to blast tiny droplets of tin with enough energy to create plasma that produces extreme ultraviolet light. That light is then bounced through a series of mirrors so precise that a single atom of contamination would ruin them. And it uses that light to print circuit patterns onto silicon so small that you cannot see them with a regular microscope. Each one costs around $200 million. They weigh about as much as 2 commercial airplanes. And they are the reason TSMC and Samsung can build chips at 3 nanometer and 2 nanometer today. Huawei cannot buy one. SMIC, the Chinese chip maker that manufactures Huawei's chips, cannot buy one either. In other words, America locked the single most important tool in the chip industry behind a door and told China it could not have the key. So what do you do when you are cut off from the most important tool in your industry? You get creative. SMIC has been doing something genuinely impressive with older technology. They are using machines called dove lithography systems, which use a less powerful type of light to print chip patterns. Dove was never designed to make chips as small as what SMIC is now producing. To get around this, they use a technique called multi-patterning, where instead of printing one tiny pattern in a single step, they break it up into several simpler steps, each one printed separately and then combined. Think of it like drawing a very detailed picture by laying down one color at a time instead of all at once. Through sheer engineering persistence, SMIC managed to push dove multi-patterning far beyond where most experts thought it could go. They reached what is roughly considered a 7 nanometer equivalent process. Genuinely impressive. But every extra step adds cost, adds complexity, and adds more chances for something to go wrong. There is a ceiling on how far you can keep pushing this approach. Huawei knew that. So their engineers started asking a completely different question. The real bottleneck nobody talks about. Here is something that surprised me when I first understood it. Modern computers are not mostly limited by how fast their transistors can switch. They are increasingly limited by how long it takes information to travel from one part of the chip to another. Think about that for a second. The thinking part is not the bottleneck anymore. The moving information around part is. Huawei says that in modern computing systems, more than 80% of energy can be spent just moving data around, not actually computing anything. 80%. The chip is spending most of its energy playing messenger, not doing math. To understand why, imagine a city. A very, very small city with hundreds of billions of tiny workers packed into an area smaller than your fingernail. These workers are the transistors. They do the actual computing, but they are connected by a network of tiny metal Rhodes wires that stretch across more than 20 layers inside the chip. Every time information moves through one of those wires, 2 things slow it down. First, the wire resists the flow of electrical signals like a narrow pipe slowing down water. Second, the wire acts like a tiny battery that has to charge up and drain every single time a signal passes through. Engineers call this RC delay. And the longer the wire, the worse both effects get. This is actually the main reason why clock speeds in computer processors have barely changed in about 15 years. We are not limited by how fast transistors can go. We are limited by how fast signals can travel between them. So here is the insight that changes everything. If the problem is distance, what if you could just make the distances shorter? Not by shrinking the transistors, by rearranging where they sit relative to each other. What if instead of spreading a chip out flat like a city on a plane, you stacked parts of it on top of each other like a skyscraper, folding the chip in half, and the number that has engineers nervous? This is the core of what Huawei announced. They call it tau scaling. The concept is actually easy to picture. Take a piece of paper covered in text. The words at the top left are far from the words at the bottom right. Now fold the paper in half. Words that were centimeters apart are now right next to each other, separated only by the thickness of the paper. Huawei wants to do that with a chip. Take a processor that would normally be laid out flat, divide the logic up, and fold one half on top of the other. Things that used to send signals across several millimeters of flat silicon now only have to send them a tiny fraction of that distance vertically. Millimeters become microns. The journey shrinks by a factor of 1,000. And when the journey shrinks, so does the delay, the energy, and the heat generated by all that data movement. In their early results, Huawei reported a transistor density of 238 million transistors per square millimeter using this folded approach. That is about 55% more logic packed into the same footprint compared to their flat design. And they are claiming that on a roadmap out to around 2031, this approach could deliver performance equivalent to what you would expect from a 4 nanometer chip, all without ever needing UV lithography. In plain terms, matching the world's most advanced chips without the world's most advanced machine. Not one specific number in that announcement caught the attention of every semiconductor engineer who saw it. Not 1.4 nanometer. The other number, 1.5 microns. This is the bonding pitch Huawei is targeting for connecting their stacked chip layers. When you stack two chips on top of each other, those two layers have to communicate constantly billions of times per second. The connections between them are tiny copper dots that bond directly from one layer to the other. The smaller those dots and the closer together they are, the more connections you can fit and the faster information can move between layers. The spacing between those connection dots is called the bonding pitch. Today, the best in the world is around 9 microns. That is what AMD uses in their 3D cache memory stacking. TSMC and Intel are in roughly the same range. Huawei is targeting 5 microns, 6 times smaller than the current best in the world, 6 times more connections per unit of area. To go from 9 microns to 1.5 microns is not a small step. It requires new equipment, new materials, new processes, and new ways of testing whether the bond actually worked. It is the kind of leap that the industry usually takes a decade to achieve one small step at a time. If Huawei pulls it off, it changes the math on everything. With enough connections between layers, the two stacked chips stop behaving like two separate chips and start behaving like one single unified, extremely dense processor. The seam between them disappears from a performance standpoint. That is the vision. But then, you hit a wall. A very hot wall. The problem that could stop everything and the honest picture. Here is where physics shows up and complicates everything. Memory chips run cool. They sit quietly and hold data. Logic chips do not do that. Logic chips switch billions of times per second, and every single switch generates a tiny bit of heat. Spread that across hundreds of billions of transistors running at full speed and you get a chip that gets very, very hot very fast. Right now, that heat escapes mostly from the top and bottom of the chip through a heat spreader into a cooling system. In a data center, that cooling system can be enormous. Liquid pipes, giant fans, entire buildings designed around moving heat away from processors. In that environment, a hot chip is manageable. Huawei's first target for this technology is not a data center chip. It is a Kirin processor. A smartphone chip. Your phone has no fans, no liquid cooling, no room for any of that. It has a thin slice of metal and maybe a small graphite sheet, and it sits in your hand so it cannot get very hot without hurting you. When you stack one hot logic chip on top of another hot logic chip, the heat from the bottom layer has nowhere easy to go. The top layer is sitting right on top of it, trapping it. You have built a tiny heat sandwich, and the filling is on fire. This is not a small engineering challenge. It is genuinely one of the hardest problems in the physical world right now. Some research teams are exploring materials that conduct heat better, or microchannels built into the silicon itself that carry cooling fluid directly through the chip layers. But none of those solutions are proven at mass production scale yet. Whether Huawei has a credible answer to the heat problem is the question that determines whether Tau scaling is a real roadmap or a very impressive sounding presentation. It is worth being honest about what this announcement actually is and is not. When chip companies talk about nanometer numbers today, those numbers are more of a marketing label than a physical measurement. 2 nanometers does not mean transistors are literally 2 nanometers wide. What Huawei is saying is not that they have invented a new transistor that is 1.4 nanometers in size. They are saying that by stacking 2 layers of their existing chips on top of each other, they can fit enough transistors into a given area to compete with what a chip described as 1.4 nanometers could do. That is still impressive. But it is a different kind of impressive. Stacking 2 mature processes does not create a new manufacturing process. It is a system-level approach, not a transistor-level breakthrough. The density numbers they are already showing from early implementations are not fake. They are just not the same thing as having a true 1.4 nanometer process. They are something different. Something that fits in a category the industry does not really have a clean name for yet. Huawei found a door in a wall that everyone else assumed was solid. Whether that door leads where they think it does is something the next few years will answer. The announcement is real. The engineering challenges are real. The outcome is genuinely unknown. And in a competition this important, being a serious player with a credible approach is not nothing. America cut Huawei off from the most important machine in the chip industry. The assumption was that without UV lithography, China could not build competitive AI processors. Huawei responded by asking whether transistor size was even the right problem to be solving. The roadmap they published puts full realization of this approach at around 2031. The 1.5 micron bonding pitch, if they achieve it, would be a genuine world first. The heat problem is real, but not impossible. And the density numbers from early implementations are already showing up in hardware that ships. Moore's Law made chips better and cheaper at the same time. Tau scaling trades cost for performance. That is a different kind of progress. But in a world where the traditional path is blocked and the alternative path is slowing down, a different kind of progress is exactly what the competition demands. If Huawei solves the heat problem and ships a folded Kirin chip that performs at 1.4 nanometer equivalent, do you think that changes the outcome of the chip war? Or does America still have moves that matter? Drop your answer below. I read every single comment.